Okay, welcome back. So I left you with the task of looking at an average separation on here of galaxies. So I just took a couple in the middle here, scaled it to the 160 arc seconds that you've got across here. I come up with 12 arc seconds, but something of order 10 arc seconds in here is fine. And so if you put that in our usual formula, that hopefully it's very familiar to you now. So L is theta d. Here I've left d in megaparsecs and just worked out theta in radians to save a bit of work. Okay, so if you're confident you know what you're doing, then that's okay. Well, anything in radians is dimensionless, so you multiply by whatever the distance is in whatever units, and it'll come out in the same units. So here it's megaparsecs. So that's 0.04 megaparsecs, which is 40 kiloparsecs. Okay. So the reason this is interesting, okay, remember that our own galaxy, the Milky Way, is only about 20 kiloparsecs across. Okay. So here, the typical separation between the galaxies in the middle of this cluster of galaxies, this very rich cluster, is not much bigger than the size of the individual galaxies themselves. I mean, you look at this picture and they look like they're nearly touching each other. That's about right. Okay, so what this means is that in these very rich clusters, the fact that the galaxies are so close to each other means they're going to be interacting with each other an awful lot, okay, as they move around. So don't forget, this is not a static situation. Basically, all the galaxies in the cluster will be orbiting around the center of mass of the entire galaxy. Okay, sorry, the entire cluster of galaxies. And so they're all moving, so they're going to be interacting with each other. And interactions leads to mergers, as we learned before. And so that leads us on to the next topic. Okay. So you can do that calculation another way. Recall that I said there were several thousand galaxies in a cluster that's only a few megaparsecs across. Again, you can do a similar calculation to what I talked about before when we looked at stars in a cluster. You can work out the number density of galaxies in a cluster. So again, if you want to do a back of the envelope calculation, if you say there are 3,000 galaxies in a cluster that's 3 megaparsecs in size, you can work out just a dimensional analysis really. If that comes up to about, well, you can work out the number density of galaxies. Okay, 3,000 divided by 3 cubed. And then it's about 200 galaxies per cubic megaparsec, something like that. And then if you do 1 over the cube root of that number, it'll give you the typical separation in megaparsecs. And that comes out at about 0.2 megaparsecs, so 200 kiloparsecs. So that would be the average separation across the entire cluster. Of course, there we were just looking at the very center where the concentration is going to be higher. But again, the typical separation is a lot lower than it is, say, in a group, like we are nearly 1 megaparsec away from our nearest big galaxy. So because the relative spacing of galaxies in clusters is small compared to the size of a cluster, then you're going to get a lot of interaction, and that leads to mergers. And recall in our previous lecture on interacting galaxies, any kind of merger activity, if you've got spirals interacting with other spirals or interacting with other irregular galaxies, so 2 gas-rich galaxies, if you do that enough, then you're going to end up with an elliptical eventually. And obviously, if you've already got 2 ellipticals and they merge together, you're just going to get a bigger elliptical, okay? Because there's no gas to do anything. You just end up merging the 2 populations of stars. So basically, if you keep merging galaxies together, you basically end up with more and more elliptical galaxies. And hopefully you could see that in the picture I just showed you, and also the picture behind me here, especially now. These rich clusters of galaxies are dominated by ellipticals because there is so much merging going on. Okay? And Another feature of merging of galaxies in clusters is that you can end up with one sort of giant, massive elliptical galaxy at the center. Again, if you read in literature, you might see this terminology CD galaxy. It's a central dominant galaxy. So you end up with this monster in the middle that's basically eating all the other galaxies that come anywhere near it, and it just grows and grows in size. Okay. So that's where the idea of a central dominant elliptical galaxy at the center of a cluster. So remember when I first introduced the idea of elliptical galaxies, I mentioned that they come in a vast range of sizes, and that's because of all this merger activity. And I told you that the biggest ones could be about 10 to the 13 solar masses compared to 10 to the 11 solar masses for like the Milky Way. So these are real monsters. So they can be hundreds of kiloparsecs in size. And they're the result of all this merging, just sitting in the middle of the potential well of this cluster of galaxies, eating all the other ones that fall into its path. So here's a picture of one. Okay, so you've got this massive elliptical galaxy, much, much bigger than the other galaxies that are sitting around it in the same cluster here. So that's the idea of a central dominant giant elliptical galaxy in the middle of a big rich cluster. So they're the biggest galaxies we know. Okay, but they're not the biggest structures we know. So there's something bigger than clusters of galaxies, and the not unsurprisingly named superclusters. So these are basically clusters of galaxies. So you can get groupings of clusters of galaxies, and these are you can get tens of galaxy clusters, all forming another larger structure, which is referred to as these superclusters. But here something different is happening. You might expect these to be even more sort of centrally concentrated, but they're not. They're sort of tens of megaparsecs across, so pretty big structures. We are actually in a supercluster. If we look on a larger scale ourselves from where we are. So recall that the Virgo cluster, which is 15 megaparsecs away from us, is basically the dominant cluster of galaxies within what we would call the local supercluster. So our local group is another structure within this local supercluster. But they aren't spherical in geometry usually. They're usually filamentary or sort of flattened like pancake structures. Okay, so all the galaxies spreading out in a line or a flattened structure. Oh, sorry, all the clusters spreading out in a flattened structure. So to see this, we really need to look on the much, much larger scales. And here, obviously you need, we're trying to make sort of a three-dimensional map of the distribution of galaxies here. So a sort of an easy way of doing that is to use Hubble's law, okay? And you just measure the Doppler shift, you measure the recessional velocity, and then you can just plot the recessional velocity and use it as a proxy for distance. Remember, v equals hd. So if you plot just velocity or redshift and plot a sort of the galaxies in a particular sort of plane, you can get a sort of two-dimensional slice through the universe. And that's what we're seeing here. So let's just concentrate on the axes here for a moment to give you an idea about what we're plotting. So every little yellow dot on here is a galaxy that's had its redshift or its recessional velocity measured. And so you can see that this is like a two-dimensional plot of radial velocity. So you go off in a particular direction and you measure the redshift of a particular galaxy so that you can plot it in sort of velocity units on this plot. So this is just a slice in a particular plane, and we are at the center of these kind of plots. So this is obviously, so we are at 0 velocity, and because of Hubble's law, the faster and faster that a galaxy is receding away from us, the further and further away from us it is. Okay, so the local supercluster, that's why I'm showing you this plot, is the sort of concentration of galaxies In the middle here, you can see it's kind of spread out in this direction. You can see here's Virgo. Well, you can't really see a concentration here, but just take my word for it. Okay, so that's a whole bunch of galaxies a whole cluster of clusters in the center of here. Our little local group is in the middle. Okay, but if we sort of go out a bit further, you can see that galaxies are not uniformly spread in here. So there is structure on this local scale. So you've got a grouping of clusters of galaxies over here. You've got another one over here, okay, and another one sort of over here at least. And they're also starting to see regions here where there isn't much going on. Okay. Ignore this kind of what looks like a sort of an empty wedge, sort of going off this way and this way. As it says here, the plane of our own Milky Way is in this direction. And because most redshift surveys for galaxies are carried out in the optical, we can't look very far we can't look past the plane of our own galaxy, the Milky Way, because again, remember those optical pictures of our own Milky Way, it's just full of dust and you can't see in those directions. So that sort of imprints a shadow, if you like, on these plots. So this is above the galaxy in one direction, and this is above the galactic plane in the other direction. Okay. But so you can think of these as a two-dimensional representation of the distribution of galaxies around us, starting here and moving outwards. Okay. So that's one way to start to reveal the distribution of galaxies, and then groups, and then clusters and superclusters. Well, it's a very good way of doing it. It's not the only way. Okay, so here's a sort of different view of millions upon millions of galaxies. Okay, so this is now a very wide field optical picture. This is basically, I think, the entire sort of southern hemisphere, if you like, of the sky, pretty much. So imagine if you could look up at the night sky with your optical eyes and remove all the stars and just leave the galaxies. This is what the night sky would look like. Okay? If you had giant eyeballs that were very sensitive and only saw galaxies and didn't see any of the stars. Okay? So this was a giant photographic survey of the southern sky, and they went around, digitized everything. In fact, these colleagues were colleagues of mine when I was a postdoc at Oxford back in the 90s, and they were doing all this work at that time, and it was quite revolutionary work at the time, a massive undertaking, and produced this kind of two-dimensional view of all the galaxies. And you can see that there are filamentary structures here. Okay? You can very clearly see filamentary structures here and here and here. So and over here as well. So this is what I mean by the sort of superclusters of galaxies having more of a filamentary type of structure. Okay. Ignore these holes here. I think that's probably just where there are bright stars that burn out the plates. But the rest of it, you see it's sort of filamentary. You can also start to see sort of regions like here and here and here where there don't seem to be that many galaxies. And we'll come on to those in a moment as well. This is a similar version of that, but now the entire sky, okay? And this is generated from this survey of Tumas, which we did show earlier when we had the view of the Milky Way galaxy. In fact, now the Milky Way is here, but that's been removed here in order to just, again, show the galaxies. So this is a near-infrared view of the distribution of galaxies in the sky. So again, you can really start to see these sort of filamentary structures. So again, I think some of the local superclusters is in the middle here, I think it's behind the Milky Way. Maybe that's the Great Wall, I can't remember. But filamentary structures here and here, and over here as well. So these are your kind of supercluster type structures, these sort of structures, and over here. And again, start to see holes where there don't seem to be many galaxies. But of course, this is a two-dimensional view, so you are stacking things up along a line of sight here. We'd much rather have a sort of a three-dimensional view. And for that, we need to go back to those redshift slices, as they are called. Okay, so this is a different view now. This is now going back to us being at the center. So you can see here the axis going outwards now is in the redshift, or actually in translated using Hubble's law into distance here. Okay, so getting up to like 1,000 megaparsecs away. Ignore these time units around the outside. They're just a way of doing astronomical coordinates in the sky. So don't worry about those. So really this is just a slice, again, starting with us at the center and going out through. And again, now you can really start, you're not stacking things up along the line of sight anymore, like in those previous 2 slides that were 2D images on the sky. This is now a slice through the 3-dimensional distribution of galaxies. And you can see these filamentary structures all over the place. Just looks like a bit of a Swiss cheese, if you know what I mean, or like a foam structure. Okay, and you know, this is what cosmologists get very excited about, because you know there is real structure out there in the distribution of the galaxies, and obviously everything is pulled around by sort of whatever gravitational forces are at work in the evolution of the whole universe here. Okay, so it's really telling you something about how the universe works, this pattern, and you know, that's the kind of cutting edge of modern cosmology, really. So this is some results from what's called the 2-degree field survey that was done by a telescope in Australia. So my colleague, Dr. Lumsden, worked on that survey when he was in Australia many years ago. And it, you know, it's still a very useful survey. So they found the redshifts of 250,000 galaxies at the time. Okay. So in recent times, it's been superseded by the Sloan Digital Sky Survey that again I mentioned earlier in the course, that has now found the redshifts of 1 million galaxies. So you can really plot these 3-dimensional maps of the universe. But something else I want to show you here is really starting to come out of these holes. Okay, so like I said, it is a bit like a Swiss cheese. And so the cheese has holes in it. And these holes are actually the biggest structures in the universe, like this one down here. So these are referred to as voids because there don't seem to be any galaxies in these holes. So this is even more sort of puzzling. You know, why are there these regions of the universe where there aren't any galaxies? Okay. I can't tell you the answer because it's, you know, that's what people are still trying to work out. So when you talk about large-scale structure, voids are basically the largest scale structures that we see. So these are up to sort of, you can get up to, well, you can see on this picture, I think. So they can be 100 megaparsecs across. Okay. So that's bigger than these superclusters, which are, you know, tens of megaparsecs long. So the voids can be 100 megaparsecs across. Okay. And the weird thing about them is that the filamentary superclusters, or pancakey structures, seem to be on the, you know, the boundary between the voids, if you like. So it's like as if something's blown a foam in the universe, and the galaxies make up the walls of the foam, or the cheese and the Swiss cheese, if you like, and then the voids are these sort of gaps in between. So like I said, these are the biggest structures in the universe, about 100 megaparsecs across. Once you get above that, the universe is pretty isotropic and looks exactly the same pretty much in all directions. Okay, so the last little topic here, and it will bring us into our final lecture, which will focus on dark matter again. And it's really the dark matter and these days, of course, the dark energy that is even more peculiar, that is shaping all of this structure. But let's just focus on something called peculiar motions here to finish up this topic. So, as I mentioned earlier, the galaxies in these clusters and groups, but particularly in the rich clusters, are moving around under the mutual gravitational attraction of all the galaxies within there. And as you now know, not really necessarily the visible stars within those galaxies, but the mass of each galaxy is dominated by the dark matter within those galaxies. And in fact, the clusters themselves contain even more dark matter on the larger scales. So basically, there's a massive gravitational potential well full of dark matter, and all of these galaxies are moving around, orbiting around that center of mass. Now, the galaxies move around within that potential well with velocities of, at least a few hundred kilometers per second for typical sort of groups and normal clusters. Recall that the Andromeda Galaxy is moving towards us in the Milky Way at about 300 kilometers per second. So that's very typical here. So the galaxies within these clusters will have their own velocities to do with local gravitational movement of a few hundred kilometers per second, typically. Now, that, what's referred to as peculiar motion due to local gravitational effects, of course, can interfere locally with the idea of Hubble's law, the idea that the whole universe is expanding in a sort of uniform isotropic manner, which is true on the largest scales, but local gravitational effects due to galaxies being members of clusters can interfere with that expansion. If you look in a particular direction of a particular cluster, some galaxies will be falling in towards the center of the galaxy's potential well, the cluster's potential well. Other galaxies will be flying out towards us. And if you measure the individual redshift of those galaxies, it will be a combination of the Hubble expansion of the universe, which in effect would be the kind of motion of the center of mass, if you like, of the cluster. But superimposed on that will be these peculiar motions, which will be in random directions due to the fact that all the galaxies in that cluster are moving around under the gravitational effect of the gravitational potential of that cluster. Okay. So you can actually see that on some of these plots. You've probably actually seen it already, but I'll point it out in an example in a moment. So this can cause errors, especially in more nearby galaxy clusters, because you get the kind of Hubble flow wrong by several hundreds of kilometers per second. And if you get the velocity wrong, in a sense, because of local gravitational motion, as opposed to the uniform Hubble expansion, then you get the distance to the galaxy wrong if you only just use the redshift. Okay. I'll point this out in the example at the end. I'm going to point it out here. Okay. So here's another of these slices. Again, don't worry about the strange time units. So this is just going all the way around the sky in a particular plane. We're at the middle again, okay? And you can see that this is redshifts out to, velocities out to, recessional velocities of galaxies out to 12,000 kilometers per second. So we're at the middle. Going around the edge is 12,000 kilometers per second, and linearly in between. You notice these structures, okay? There seem to be these funny looking linear structures here that point back to us. So here's another one, there's another one, there's another one, okay? So you can see these sort of a bit like spokes on a wheel. Okay? And these are due to the fact that all the little dots here, these are individual galaxies, all with their individual recessional velocities measured. But you can see that if you've got a concentration of galaxies in a cluster, suddenly that causes the cluster galaxies to all spread out in a radial spoke pointing back towards us. Now this is not real, okay? It's not that we're in a special point in the universe and that all clusters of galaxies are strangely elongated along our line of sight. It's because of the gravitational effect of the cluster. So these are really the peculiar motions superimposed on top of the Hubble expansion of the universe. So the center of the cluster would really be sort of here somewhere, but the galaxies on this side are somewhat blue shifted compared to where they ought to be, because they are falling back towards us giving us a little bit of an extra blue shift on top of the general redshift. And the galaxies on this side of this distribution here are moving away from us because they're falling into the cluster. So these are probably preferentially actually on the near side of the cluster, and these are probably actually preferentially on the far side of the cluster, sort of counterintuitively. But that stretching out there by whatever it is, several hundred kilometers per second, is the effect of the peculiar motions stretching the distribution of galaxies out along the line of sight. So don't forget that this is not really distance that we're plotting. We're using the velocity or the redshift as a proxy for distance. And so when you've got these peculiar motions in rich clusters like here and here, you get errors in the distances. Now, this phenomena is in these plots, these redshift slice plots as they're called. It's rather prosaically referred to as fingers of God. Cosmologists like to bring God into things, because they all look like they're pointing back to us in a sort of a eerie way. Okay. But it's not a real effect, it's just the peculiar motion effect that we just talked about. Okay. So let's summarize the large-scale structure. So we worked our way up. So most galaxies are in groups or clusters. So the groups have tens of galaxies, the clusters can have thousands of galaxies, and we are in our own little local group. The clusters of galaxies can end up in superclusters, so clusters of clusters. And all of this structure, which these get a bit filamentary and pancakey and surround these voids, which appear to these like foam-like bubbles in the universe where there aren't any galaxies in them. Okay, so this is all the rich tapestry of the large-scale structure of the universe, which is driven by the cosmological effects of dark matter and dark energy in the expanding universe. And all of this points back to physical processes that we don't really understand yet, that basically happened in the Big Bang and the subsequent evolution and expansion of the gas and eventually the galaxies under the effects, of gravity and basically all the dark matter, dark energy stuff that we don't even understand. Okay. So let's finish up. So a little problem for you to have a look at is to go back to that last redshift slice that we looked at. And again, you can tell by now that I like you to get a pencil and ruler out and measure a few things off some real data. So pick the most extreme cluster of galaxies on that slice. I'll show you again on the next slide, and estimate the error in the distance due to the peculiar motions of that particular cluster. Okay, so let's show you what I'm talking about. So this is the most extreme one here. So you can see this highly elongated structure here. So the biggest set of peculiar motions due to a very concentrated rich cluster of galaxies here. So recall the scale, we're at the center. So that's where 0 kilometers per second in terms of velocity is. And the edge of this circle is at 1200 kilometers per second, as you can see up here. So you can work out the distance to the galaxy just by sort of estimating how far along this line in velocity we are. Okay, and then you can make an estimate of the peculiar motions, so basically half the distance of this. Okay, and that would give you a typical uncertainty on the distance if you were using Hubble's law to measure the distance to individual galaxies in this cluster. Okay, so if you can have a go at that, this will also lead us nicely into another way of looking at dark matter next time, because it's dark matter that is dominating the gravity in these clusters. And that will be our final topic. Okay, so we'll stop there.